All right, so this last example, I have started it and scaled my y-axis in thousands. Started at 7,000, increased all the way up to 16,000. Years, I chose to go 10 years. Each tick mark represent 10 years since 1900. Remember, there's more than one way to do this. You want to just try to make sure you use almost all the tick marks if possible. I'd encourage you to try to do some of this before I post the answers. So I'm going to go ahead and do this scatter plot here in just a couple of seconds. One thing you might do off to the side of years is just write, these are the X values that are going to represent each of these years before you do anything else. We don't need to do that with the Y values. So I've got my data plotted, and a couple things I want you to notice. So I chose to do years since 1900, and I started back here at 1910, which is okay, but the only thing is, then what happens is the data kind of gets scrunched together, and it's just kind of in between these two bars instead of using the width of the entire graph. So that's why it's important. I wanted to show you why it's important to pick good numbers to count by on the X and Y axis. So this one I feel like is pretty obvious that we're going to use a quadratic function. It takes the data takes a dip, and before it starts to increase radically once again. So I'm going to use a quadratic function that goes through as many of those points as possible. And we're going to get the equation for that quadratic. So next you want to enter all of the data into your calculator to get the equation of the curve of best fit. Again, just one thing I want to show you, if you did not reset the calculator's memory, scroll up to L1, hit clear, hit down. Scroll up to L2, hit clear, hit down. If you reset the calculator's memory, don't forget to go back to mode and turn your stat diagnostics on. So there's the X values in L1, and there's the Y values in L2. Again, really important you get those points right. Even one number being off can affect the equation quite a bit. So now we're going to go to Stat, scroll to the right to Calculate, and we're going to choose number 5 for quad regression. And there's our equation. And again, I like to write out 3 decimal places. The more decimals you write, obviously, the better. But do at least 3. So there's our equation. And I'm going to go and type that into y equals. Before I do anything else, I'm going to clear out the last equation I had and type in this equation. And then just always is a good way to check to see how things are going. Hit zoom 9 with your plots turned on, and then you can see the data points match up pretty similar to the data points we have on our graph over here, and that curve looks like a pretty good fit. So number 3 says, according to the curve of best fit or model, what was the least number of homicides in the US, and when did this occur? So essentially we're coming up with the vertex. And you could use the formula for vertex, negative b over 2a, and then take that negative b over 2a and substitute it in for x. That would certainly work. But I'm going to lean on the graphing calculator as much as possible. So I'm going to use before I do look at the table, I just want to take a quick look at about where the vertex looks like it exists. It looks like somewhere around 1950. And of course, this is a very approximate sketch. But that tells me when I go to my table, I want to scroll to where x is 50. And remember the shortcut, second window, and you can tell your table you want it to start at 50, or I'm going to use 40, a little bit before the vertex, and then go back to the table. And basically we're looking for where the Y value dips and then starts to recover and then starts heading the other direction. So you can see the number of homicides are going down. We're looking at the Y column to come up with that. And then it looks like right here, 1951, that seems to be the bottom, because then we start to increase on the other side. So the least number of homicides occurred in 1951, and it's roughly 6,873. All right, so that's number 3. Number 4, how is this point evident on the graph? Well, we kind of talked about this already. It's the vertex, or the lowest point of the graph. Number 5, what is the algebraic domain and range for this function? So the algebraic domain for this function would be like if we treated this equation that we came up with just as a general problem that didn't necessarily represent a real life situation. It would be as if we looked at this curve and we saw, well, this curve is going left infinitely and it is going up and to the right infinitely. So the algebraic domain for this graph is all real numbers, or we can say negative to positive infinity. The algebraic range would be whatever this lowest Y value is, which we just came up with. The lowest Y value was 6,873. So we're going to do a square bracket around 6,873, and then it goes up to infinity. And again, we call this algebraic because since this is a real life situation, a range of infinity homicides doesn't really make a whole lot of sense. And that's what we're going to tackle in number 6. What would be an acceptable real life domain and range for this function? Explain your reason. Now there's lots of differing answers here that you could put for domain. Some people would make a case you could put negative infinity to positive infinity for domain, since this represents the year. So you could say all of the domain is all of time if you go negative to positive infinity. I'm going to keep it inside this century. So I'm going to write the domain from 1900 or year 0 to the year 2000. Just because at a certain point, this model would need to be tweaked to kind of meet the needs of the time we live in today. And then again, the range, I'm going to use the same bottom point, 6,873. But then we have to think about what is a realistic high number for the number of homicides. It's obviously not going to go up to infinity. The highest number we have recorded in this table is almost 17,000. But we definitely have a trend from this data that the number of homicides is going to continue to increase. So for the range, I'm going to go with a high number of 50,000. And even though if you go back and look at the table, 50,000 is a lot higher than the all-time number of homicides we've had in a year, that's just to make sure we fit all the data. All right, number 7, what is the y-intercept for the curve of best fit? To find the y-intercept, we need to find the point where x is equal to 0. So the easiest way to do this is to look at our table where x is 0. So I'm going to go back to second window, and I'm going to do my table start of 0. And we go second graph to look at the table. And we see at 0 we have 56,393. Number 8, what does the y-intercept represent in real life? Keep in mind the year 0 represents 1900, so in the year 1900 there were 56,393 homicides according to the model. Number 9 says how many homicides should have occurred in 1976. So they give us an X value of 76. We need to find the corresponding Y value. So one more time, second window. Let's tell the table to start at 76. And then second graph, and we can see where that number is. In 1976, there are 21,618 homicides. And again, this is according to the model. And then finally, it says, according to the curve of best fit, when should 20,000 homicides have occurred? So this time they give us the Y value. So Y is equal to 20,000. We have to find X. So you can see already we're pretty close at 20,000. So if we just scroll back just a couple of years, really, and we will see it looks like not 1974, but 1975, we've eclipsed that 20,000 mark. All right, and it'll be good to know that actually the number of homicides today in 2020 is lower than this number that was represented in 1974.